Hello, everybody, and welcome to another edition of Dome to Home. Rémy, you want to take it away?
Hello, absolutely. Hi, like I said, welcome back to Fiske Planetarium's Dome to Home Summer Series. We'll give people just another moment to sign on and refresh the page if they need. But in the meantime, my name is Rémy. I am an astronomy student at CU Boulder and a presenter at Fiske Planetarium. Below me, we have...
Hello once again, everybody. My name is Jeremy. I am a CU Boulder alumni, and now I work as mainly an outreach presenter and navigator. And in these tumultuous times, I've been working more on getting all these kind of virtual things, all these products that we're trying to keep pushing out to you guys to keep you guys looking up at the skies and engaged in space.
Yeah. So Jeremy's our navigator today. Everything that you see over there on the dome, that is all Jeremy. He does this all live, which is amazing. So our navigators are the best. So if you are watching us live, be sure to hop on the chat down there. If you have any questions, send them there, and our question master and chat moderator, Tara, will pass them off to us to answer live in the video. If you're watching after the fact, feel free to leave a comment or come back for the next Dome to Home. So it sounds like we've given everyone some time to sign on, so let's go ahead and get going. So today we'll be learning some of the weirdest facts about black holes. So they're some of the strangest objects in the universe, which means we have a lot to work with here. But I'll try to condense it as I can. So let's start with weird thing number one. So some black holes are dead stars. So stars, you may have heard of them, they're giant element factories. In the core of stars, there's so much heat and pressure that light elements fuse into heavier elements. So at the center of our sun, there's hydrogen fusing into helium. And as you get further in a star's life, they start fusing heavier elements until eventually the star can't fuse anymore. It's dead, Jim. So the larger the star, the more elements it can fuse. And there are some really big stars. So we can take a look at some of these really big stars, because when you look in the sky and you see all those little dots, it's not very, I think it's exciting, I think it's cool, but you can't really get a sense of just how big some of these stars are. The sun is actually a pretty medium, small size star.
Take you over and fly on over to the sun so we can start taking a look at some of the different sizes of these stars. Here we are.
There we go. So we've got the sun. We've got a few other stars that we can pull up here. So the first star we're going to pull up is called Sirius. It's the brightest star that we can see from Earth, but it's only the brightest because it's pretty close. It is a really hot, really bright star, but there are stars that are brighter. But you can see Sirius is a bit bigger than the sun. It's about 2 times the mass of the sun. We have next on our little list, Aldebaran. So here's Aldebaran. Aldebaran is huge, but it's still a little less than 2 times the mass of the sun. That's because it's on its way to dying. It's in its last stage of life when it starts puffing out and expanding. So even though it's not terribly much larger than the sun, it's a lot bigger. So we have after here, we've got Rigel. Rigel is really, really big, really, really massive. It's about 18 times the mass of our sun. So they're 18 times the sun here, just in Rigel. We have next Betelgeuse. And Betelgeuse is also, you can see it's huge and red giant. It's on its way to dying. It's about 11 times the mass of the sun. And then we have the largest star that we know of, which is called NML Cygni. And we're going to have to zoom out pretty far to really get a sense of how big this star is. It's huge. There are the planets right there. How far out is that? That's about the orbit of Saturn, past there, yeah?
Yep, so that outer yellow ring, or the outer yellow ring within that yellow star is actually the orbit of Saturn. So this is a very massive star, very big.
So yeah, this star is about 50 times the mass of our sun. So the more massive stars like Rigel and this NML Cygni, they burn through their fuel really quickly. but they make more and more elements because they have lots of heat and pressure in the core. So those stars do hit a point, though, that they can't go anymore, and they end up collapsing in on themselves and then exploding into a supernova. So not every star is going to become a supernova, but ones like Rigel and that NML Cygni 50 are going to be supernova. So that puts a lot of pressure on the core of the star, compressing it. So if a star is massive enough, specifically like NML Cygni, and it creates a powerful enough supernova, then it compresses the core past physical space into a black hole. So these small stellar mass black holes are actually dead stars, star corpses. So then the question is, what is a black hole? So let's go to weird thing number 2. So not even light can escape a black hole. So that's pretty much what the definition of a black hole is. It's an area of space that is so compressed that its escape velocity is faster than the speed of light, which means that there's so much gravity that nothing can leave it. So the same way that I can't just jump off the Earth, light can't leave a certain distance from a black hole. So there you can see in the center is the singularity, which is the point, the center of that black hole. And that red circle you're seeing around that says horizon is what's known as the event horizon. That's how far away you have to be, where the escape velocity speed of light. You have to be going the speed of light. To get away from that point and inside it, you have to be going faster than the speed of light, which is in fact impossible. So let's see. You might remember that stellar mass black holes are dead stars, right? So this means that those black holes are actually less massive than a star. And stars shine, so they definitely aren't black holes. So then how would something with less mass have more gravity? So gravity doesn't just depend on mass, like how much stuff there is. It's really important, how much stuff, but also important is the distance, how close you can get to an object. So the further I am from Earth, the less gravity I feel. So you actually weigh less on top of a mountain than you do at sea level. But there's only so close I can get to the Earth because the surface is in the way. I can't get any closer to the mass of the Earth than right here on top of it. But what if I make Earth smaller and give it the same mass? It means I can get even closer and closer and feel more gravity. So black holes are extremely small. They're infinitesimally small, which means I can get pretty much infinitely close. So we've got these gravity wells pulled up here. So the spread out masses, like the sun here, it just makes this nice little dip like this, these smaller dips. So these compressed ones, like a neutron star, which is another type of star corpse, where it just isn't quite powerful enough supernova to get a black hole, it's still really compressed and dense, makes a much bigger dip. And then you have a black hole here that just makes a huge dip. So that gravity increases, increases, increases as you get closer and closer and closer. And the dips show how tough it is to get away from that object. So the black hole in the end, it's tough enough that not even light can get out of there. If it gets close enough, it's just never coming back. So then how do we know black holes even exist if there's no light coming off it? So weird fact number 3, black holes are some of the most energetic phenomena in the universe. So for something that eats whatever gets too close, they do actually make a lot of energy. And that's because black holes, they're really messy eaters. So material falling into a black hole ends up spinning around like water going down a drain because the target, it's just so small. It doesn't all just fall into this tiny target. It's all going around as it swirls around, it heats up, gains energy, and spits it out. Like a jet, like you see right there. So we like to look for really bright sources of energy, especially in X-ray light. So X-ray, because it's really, you have to have a high energy, high temperature to be emitting X-rays. So here we have an example of an X-ray emission that we believe might be from is from what's called a black hole binary. So that's a black hole, it had a companion star, and now it's eating that star. So this is Cygnus X1, and it's the first confirmed black hole. And I think we have in there what it might look like.
Yeah, so here is a nice artist kind of representation of what that might look like.
So you can see there's its companion star, and they're orbiting around each other, but that star is close enough that that outer material is getting pulled into that black hole, swirling around and spat out with those jets. So we have a few other examples of jets that we see.
Yeah, and just real quick, I did want to bring up one other thing, if I may, Rémy.
Oh, absolutely.
Just the catalog of all X-ray sources that have
Ooh.
been found in our galaxy, and maybe I'm not sure if any of these would be out of our galaxy. Probably, maybe. I don't know. What do you think, Rémy?
So these ones are just like X-ray sources in general. So some of them might be outside the galaxy, some of them might be neutron stars, but a lot of them could be black holes. So finding an X-ray source means that it's possible that it's a black hole. It could be some other stuff. So it just takes a little more studying to figure out if that X-ray source is a black hole or something else. So we have our fourth weird fact here. So black holes can be millions or billions of times the mass of our sun, like this right here. So earlier I said that there are two types of black holes. So you may have noticed when I said stellar mass black holes, some black holes, smaller black holes. That's because there's a second type. It's called supermassive black holes. So these stellar mass black holes might be a few dozen times the mass of the sun at their largest. These supermassive black holes, like you see right here, are millions of times the mass of the sun at their smallest. So you can see here that, like I said earlier, really energetic, messy eaters jets, that jet is thousands of light years long from this galaxy, M87. So here's a weird fact, I suppose, for B. We're not really 100% sure how these ones are made. So supermassive black holes, they're another type, they're amazing, but we're not 100% on how they even get there. So they might have been made early on in the universe with huge stars that ended up eating enough material to get that large. Could be some other things. And there are tons of them, though. In fact, weird fact number 5, there's a supermassive black hole in the center of most, if not all, galaxies. That means that, yes, there's even one at the center of our galaxy. And we know this by tracking orbits of stars nearby. Ooh. Yeah, so all of these galaxies that Jeremy has pulled up here have a supermassive black hole in the center. So we confirmed that with our own galaxy. What we did is we tracked orbits, stars nearby the center, like in the center of the galaxy, and you can see right there. So you can watch, there's the time in the corner there, what year all these data were taken. And you can watch these orbits as they go around. And by tracking these orbits, we can tell how fast they're going. And by seeing how fast they're going, we can tell how much mass it's orbiting. So we don't see anything there. It's a pretty small space for there to be nothing. And doing all that fancy math, we find out that the only object that could be in there is a black hole, about 4.5 million times the mass of our sun, but within the orbit of, I think it's Mercury.
Pretty weird.
So yeah, that's why we're here with the weirdest facts about black holes.
Yeah, exactly.
So you remember that galaxy with that huge jet, M87 with its huge jet? It's thousands of light years long. We actually have a closer picture of it. You might remember this from last year. It's the Event Horizon Telescope picture. Oh.
Sorry, I thought you were
wanting
to see the jet again, but that's the jet we're talking about.
I always want to see the jet. I love that picture.
Here we go. Maybe this is
there it is. Yeah. I'm looking for the Eye of Sauron over here. Yeah.
There we go.
So this is the Event Horizon Telescope picture. Jeremy's great. He's got all the pictures there. So what we're seeing here is the material swirling around that black hole that is in that galaxy all the way over there. But what we're seeing isn't that top-down view. So remember before when we had that picture and we saw that there was that disk swirling around, this isn't just a top-down view. This is that we can see behind it. So here is weird fact number 6, black holes bend light so that we can see behind them. So what we're seeing isn't like a hula hoop, this is what we're looking at. So you can see the light from behind this black hole. So light gets bent around it. It's not always falling all the way in if it's still far enough away. And we end up seeing things that we wouldn't see otherwise. So light from behind gets bent over, light from the left gets bent around the right. We get a pretty odd picture. So if you've seen Interstellar, and I think Jeremy had the picture up earlier, you might remember how that black hole looked. There it is. So what you're seeing isn't a halo behind it. What you're seeing is the other part of that disk, but the light being bent around. So you can see the top of the disk and the bottom of the disk that's actually behind the black hole. And that's called gravitational lensing. So it's one of the ways that we can kind of see when there's mass there. Black hole does that. There are also examples of galaxies that we see having this lensing effect, but that's usually from, like these pictures here are from dark matter, but it's that same principle where light from behind is getting bent around.
Yeah, and this is one of the weirder phenomenons in the universe, in my opinion, because it has the ability to make some really strange looking features when we look up into the nighttime sky. Like this is one of my favorite examples of gravitational lensing, because it looks like a little creepy galactic smiley face staring back at us.
It does look like a smiley face. I love that picture. So we have our 7th weird fact. I can count 7, that's 7, is that black holes can merge, actually. So 2 stellar mass black holes orbiting each other. So remember, there were those binary systems where there's the black hole and the star. What if we had 2 black holes? And they orbit each other, and it causes a lot of weird distortions in space, kind of like throwing a rock into a pond. So you can see them kind of swirling around each other. And I love this video because you can also see all that light around it getting bent, like we were just talking about. And they twirl around each other, and eventually they crash into each other. Their orbits decay enough and become one larger black hole. And these distortions, they go out like the ripples in the pond when you throw the rock in there, and we can actually detect that. So these are called gravitational waves, and we can actually detect them here on Earth with an observatory, I know how to talk, called LIGO. So there are 2 locations where LIGO uses very precise lasers to show changes in distance when a gravitational wave passes through. And we can map those out, and then we can actually listen to a black hole merging. So it kind of sounds a little bit like a chirp. I think we have them here, yeah? Yes. So you can see there, the ripples getting more and more as they get closer and closer, and then that merge right at the end.
We'll play it one more time for you, because you might need some folks might need to turn up their volume a little bit. It's kind of hard to hear.
Hopefully you can hear that okay. Yeah, so that's actually really recent development. We've only been listening to these mergers, to these gravitational waves for the last 5 years, which, considering how long we've been doing astronomy, isn't very long at all. So 8th and last on our list of weird things is actually a question that Denise asked here in the chat. What happens if you fall in a black hole? A lot of weird stuff happens when you fall in a black hole and when you get close to it. So a few of the more interesting, the weirder things. For one, time actually slows down for you. So gravity slows down time, and that has to do with those curves you saw earlier. So light is constant. The speed of light is constant, but it has to travel farther when it's closer to large objects because of that big distortion. And that leads to more time having to pass there versus further away. So not only do you weigh more at sea level than on a mountain, but your time is moving slower. It's not quite enough for an effect on us to notice in our daily lives, even though GPS does have to factor it in. So we don't have to adjust our clocks every time we go up a hill. But near a black hole, that distortion is huge and very noticeable. So if someone was watching you approach a black hole, they would see you moving slower and slower and slower. And if you were looking at them, they would seem to move faster and faster and faster and faster and faster as you got closer to that black hole. So that would be pretty neat to see, honestly, wouldn't it? But don't get too excited just yet, because there is another effect that might ruin your plans.
My favorite pasta dish.
You'll get a plate of spaghetti. No, you have to eat spaghetti if you get close to a black hole. Now, what happens is you get stretched out like spaghetti. So you know how we talked about gravity? It's stronger closer to an object. So for something like these stellar mass black holes, it's so much stronger with even a very small distance. So if you're falling feet first into this black hole, the gravity on your feet is a lot more than the gravity on your head. So it's getting pulled a lot more than your head. And that means your feet are getting pulled away faster than your head, and you get stretched longer and thinner like spaghetti. And that's why astronomers literally call it spaghettification. That's the technical term for it.
We're good
It's
at
one of
coming
my
up with
favorites.
names.
They really are. We've got great names. We've got cool stuff like spaghettification and galactic cannibalism, but then we have like very large telescope. You know, it's a grab bag on names. But spaghettification, despite the cool word, does not sound very pleasant. So although black holes are super weird, super interesting, I wouldn't recommend visiting one too close. But since you can't visit one, Jeremy and I are going to do the next best thing, and that is answer your questions. So if there's anything that you want to know about black holes or just anything that comes to mind, let us know right down there in the chat. And if you want to make fun of me not being able to talk, go ahead and feel free to do that as well. So that's what's fun about doing these streams live. You get to hear me mess up, and you get to ask questions, and we can find out what you want to hear too. So if you have any questions, pop them down there in the chat.
While you're coming up with some of those questions, I'm just going to bring up the X-ray catalog again and then circle some of the ones that we were talking about. So if you look kind of towards the center right of your screen, you'll see that bright X-ray source, Cygnus X1. And then, as Rémy mentioned earlier, we also have Sagittarius A star located at the very center of our galaxy, coming up on the right-hand side over there now.
Sagittarius A star, that's the name of the black hole in the center of our galaxy. It's called that because it's found in the direction of the constellation Sagittarius. And it's A because it was first one. And then you call it star. They added the star on the end because it was exciting to find. So we've got a question from Amanda who wants to know, can you tell me about wormholes? How do they happen? We can tell you about wormholes. So wormholes, in case you aren't familiar or haven't seen any sci-fi or whatever, it's this concept that you've connected 2 points in space that are next to each other. So by going into one end of the wormhole, you come out the other end somewhere else. And those kind of connect to black holes. A lot of people kind of think of black holes as maybe it's a wormhole. You get sucked in one side and spat out the other side. We don't have evidence of that being real, as extremely cool as that would be. We can do some fancy math magic that we like to do to make a wormhole work and make sense. So you might have seen a wormhole in Interstellar that we were talking about before, or Star Trek has wormholes, that sort of thing. Unfortunately, we don't have that right now. The concept, though, is that you have 2 points in space, and this black hole maybe is just connected to another point, and you can go right through, kind of like a bridge or a passageway. I would love to know how they would happen so that I could make one. I don't know about you, Jeremy.
Oh, yeah, that would be awesome. I'd be the first to volunteer to get out there.
Yeah, definitely. High on the list. So while we wait for if anybody has any other ones, I do have some common questions I've been asked. So we were talking about Sagittarius A star. Some people get really concerned and they start asking, like, are we going to be swallowed by the black hole in the center of our galaxy? It's so close to us. It's just right over there. So Sagittarius A star is about, 70,000 light years away. Remember how gravity gets less and less and less as you get further and further away? The reason that we're orbiting the center of the Milky Way is because of how much stuff is just in between. It's not necessarily just because of that black hole. We're not going to fall in anytime soon, the same way that we're not falling into the sun anytime soon. So don't worry.
Try not to worry too much. There's other things to worry about before you start worrying about that, huh?
Just a few things.
Just a few.
Can confirm as a serial worrywart.
Let's see, other questions, anything else? Any burning black hole questions that you might have out there?
But while we're waiting there, I want to point out something here about our galaxy. So you can see this big yellow light in the center there, right? So when you kind of see the galaxy edge on, you've got the flat bit, and then you've got this big circular thing, and it looks like a solid object, like it's a giant bright yellow star or something, but that's not what it is. So sometimes when you look at a galaxy, it looks like a solid structure, but it's actually a bunch of old yellow and red stars that are just, it's far enough away that it looks really compact. So same way that when you see a car really far away, it looks like one headlight, so it gets closer and you see two. All those stars are just close enough together. So behind the scenes, we've got a question. Why don't we see any middle-sized black holes? I mentioned stellar mass and supermassive. Are there any in between? Great question. So that is called an intermediate sized black hole. And we don't know of any, actually. That's a really big mystery that we have. We've got these stellar mass black holes from dead stars. We've got these super massive black holes that are from who knows what, that are at the center of galaxies, but there really isn't anything in between. You don't see something that's like 1,000 solar masses. It's something we're keeping an eye out for, just to kind of see if we can find something like that. Maybe it'll start solving some mysteries of how those supermassive black holes come to be. So that's a pretty neat thing that keep an eye out for. Maybe we'll find those one day. I've got a question from Denise, who wants to know, could the Big Bang have been a black hole? That's a fun concept. That's a really interesting concept, because the Big Bang is the concept for the beginning of the universe. All matter and energy was condensed to this single point, which sounds a lot like a black hole. All this matter and energy is condensed to a single point. And a black hole, or the Big Bang, it exploded outward, hence Big Bang. It was big, there was a bang, something like that. And it ended up becoming the universe. And it's expanding still to this day. So, you know, it's kind of black hole-esque. Like the concept is sort of like a black hole, in that it was all compressed in one point. I can't confirm that it was at one point a black hole. I wasn't there. Fun fact. Were you there, Jeremy?
Unfortunately, no, I wasn't around for that.
Bummer. So Tom wants to know, won't the entire universe eventually end up as one big black hole? So a couple of neat things there. First off, like I said before, universe is expanding and the universe continues to expand. So things are getting farther and farther and farther away from each other as a whole. So to make a black hole, you'd have to then compress it back in on itself, which it's not going to happen anytime soon because of this force called dark energy, which is just a mystery that makes the universe expand. So because of that, we've got our universe expanding, so it's not going to collapse into a big black hole. However, if you calculated all the mass and the energy that's in the universe and decided to figure out how large that like event horizon would be, how big of a black hole it would be, it's about the size of the universe. So maybe it already is one big black hole. Who knows? Mr. McFarland asks, what distance does energy directly emitted by a black hole continue to travel out into space? And is it field in a particular shape? So black holes don't directly emit the energy. It's just the, like that accretion disk, the disk around, and the jets. And it's just gonna keep going because it's just light that we see. So as far as distance, I mean, quasars is it's a type of galaxy extremely far away with really, really active black holes. And we can see those billions and billions of light years away. Like what, 12+ billion light years away? So we're seeing things that are really early on in the universe, within the first couple billion years of the universe existing. So that energy emitted by black holes can go a pretty long way. Let's see. So any other questions, toss them in really quick. Otherwise, we're going to go ahead and wrap it up. Thank you all so much for tuning in today. So if you're looking for more activities, we have a few suggestions in the video description, along with our weekly social media challenge. So we talked about how black holes are hard to see directly. Scientists have to look for indirect evidence like jets or moving stars. So the question is, can you find something that you can't see directly but know is there from indirect clues? If you can, take a picture and go ahead and tag us. So if you enjoyed this video, definitely don't forget to like it and share it if you have a friend who wants to learn more about black holes. And be sure to also subscribe to Fiske Planetarium and turn on notifications to get alerts for more videos like these. So next week, it's Jeremy and Sophie. They'll be here teaching you how to take a picture of your night sky.
Which is a very relevant topic right now. Some of you might have heard of comet Neowise coming by.
Yes.
It's great timing to be out there and try to take some pictures. So hopefully we'll be able to catch the trail end and give you guys some tips and tricks to go out and take some pictures of it. I think it'll be back around in like 6,000 years. So now's the time.
Now's the time, or you can come back in, 6,800 years and see it then.
Exactly.
I'm planning on being around for sure.
Oh yeah.
But yeah, as always, from all of us here at Fiske, thank you so much for joining us today, and we hope to see you next week.
Yeah, thanks everybody.
Bye.